Hello, I'm Matthew Weston, and today I'll be presenting Echelon, an AI tool for clustering student-written SQL queries. My co-authors are Haorong Sun, Geoffrey Herman, Hisham Benotman, and Abdul Alawini. I'll begin with our problem statement. In the field of computer science education, instructors often rely on auto-grading systems. Typically, these operate by running the students' submitted code on a series of test inputs and comparing it to a set of known good outputs. This does evaluate whether the student's output is correct on these inputs, but it does not measure the student's understanding of the code, the student's understanding of the language, or the student's ability to extend what they've done to other languages. The inspiration for our research, in fact, is the tendency of some students who are struggling in a class to repeatedly iterate on a solution they don't understand until it returns the correct grade from an auto-grading script, inevitably often resulting in a SQL query that is very malformed, overly complex, and not understood by the student. Our ideal here is to develop a way to quickly go through the submissions by the students in the class, denote every major approach taken, and iterate through them, describing what went right and what went wrong with each approach, while it's still fresh in students' minds. Our goal is triumvirate here. We want to quickly process large data sets of SQL submissions. That is, say we have a class of 400 students, we want to put their SQL submissions in, and maybe 30 seconds, a minute later, get out an easily understandable, easily usable output that we can use to run through their solutions in a matter of minutes or seconds shortly after they make their submissions. Secondly, we want to parse these submissions and provide an analysis that a professor can use to easily identify clusters of poorly designed SQL queries. Basically, if a class takes 10 different approaches, even if every individual student's code is slightly different, we want to be able to say, okay, here are the 10 main approaches, and here are examples of each. Finally, we want to allow intuitive viewing of and sampling from our clusters. That means if we select a cluster associated with a given approach, we want that process to go very smoothly, and we want to be able to get a set of the most representative queries so that a professor can go through them, immediately get a handle on what those students were thinking about and how they view the problem, and then explain what the best way to address their approach is to the class. Echelon is our solution to that problem. It takes a list of SQL submissions of any size, identifies the key approaches taken by students, and then breaks it down into clusters. As you can see in the background, we have an interface that divides our set of submissions into clusters and allows you to sample from a cluster that is selected. Before I go any further, I'll explain where I got my data, or where we got our data. Firstly, we obtained a set of submissions from a database class taught by Purdue professor Hisham Benotman. Secondly, we obtained a series of longer queries used to train the system from a database systems course from Professor Alawini. And yes, we've used several of these queries to train our system and several to evaluate it. Now, demonstration prompt from the first data set. We want to write we asked students to write a SQL query that examines a database of job applicants and companies and locates the companies that hired applicants who were at the top of their class. I'm going to open up Echelon now and run you through a demonstration of how we would parse student submissions and address them to the class. We are now in the Echelon interface, and I have uploaded the dataset associated with the question I mentioned, and here it is on the screen. Right now you see a bunch of green dots. These can be color-coded by correctness if you have that data. We did not have the data for this data set, so every dot is being rendered as green. Let's make it a little more interesting and select the optics clustering method. We now see the fundamental several approaches broken down by color. Shifting to aggregate mode makes this a bit easier to parse. You can now see that there are 6 core approaches taken by students, and for the sake of time, I will parse I will demonstrate the way an instructor would go through a lesson plan for the top 3. We'll start with the orange in the upper left corner. As you can see, the SQL queries in this cluster are different in composition, but similar in structure. Each of these is composed of a select statement, followed by a series of subqueries and from and where statements. You can see a pattern with the top ones: select, from where, or select from where, select from where, select from where. Obviously, this is an excessively complicated solution, and you can see sort of what the student's mindset is. Just creating a sort of matryoshka doll out of the question, where the core is select the max grade, and everything else goes upward from that. That's considerably more complex and considerably less efficient than what we designed for, so an instructor could take this entire group of submissions as a single entity, address that, and go through it before moving on to the next cluster. Next, we see something similar, somewhat, as evidenced by the similarity in their position in the PCA projection here. But you do notice a core difference. Where the other had a where every other line, this pattern is select, distinct, or select, from, join, select, and so on. There's no where clause, it's just joining. Now this is somewhat less ponderous way of getting to the same approximate approach. A professor could tie these two together, explain that while different in appearance and somewhat different in structure, they suffer from the same core flaw. Finally, we'll go to the third, and as you can see, it captures a, again, very different looking set of queries. This series of queries is generally formatted as select from, then a subquery, select from, aiming to get the companies where, and you can see here, there's this join statement on the last line that ultimately intends to find the company whose grade matches up with this subquery designed to try to locate the maximum grade. And again, you can see a large number of students submitted, but a huge chunk of them can be broken down into these core approaches, allowing a professor to efficiently go through the various approaches taken and address every student, or at least a large, very significant chunk of the class, on a level that feels personal without taking an undue amount of time, resources, and effort. I will now return to the presentation to go over the structure of our system and any future work that we might be working on at present. Alright, now that you've seen our system in action, you may be interested in a quick overview of how the system works, how the data flows within the system. So this diagram, as you've seen in the paper, demonstrates how that works. We begin with a SQL query. For our purposes here, let's start with a very simple query. Select 2 columns from a table. There are 2 main feature extractors, and we concatenate their extracted features to create create a final feature set that is then clustered and reduced to 2 dimensions afterwards through principal component analysis. On the left, you see our recurrent feature extractor, where we first break this SQL query down into its core elements. Essentially, we tokenize it, changing column names to column, table names to table, and all other variables that may change from question to question to generic terms. This allows us to train a machine learning model as a feature extractor on some proxy for query goodness, in our case correctness, and then lop off the back half of that model, as those of you who are familiar with computer vision might recall from object detection models like faster RCNN, so that we can then put arbitrary new SQL queries in and get a set of meaningful features out. So here we tokenize, here we switch these tokens with their indices in our list of tokens. We then feed that into a recurrent feature extractor composed of a LSTM module. These are commonly used for NLP, or natural language processing. And on the other side, we feed the original query into a structural feature extractor, which is simply a bag of words model that operates by taking the word counts from each query and giving us a notion of structure. Concatenating them gives us a solid structural representation, keyword counts, etc., from the query itself, plus more subtle features that relate to how likely a query is to be correct, which we believe at least correlates with quality, even if it doesn't always match up with it, as previously discussed, and eventually giving us the best of both worlds. As I've said, we cluster this, run it through principal components analysis, and feed it forward to an interactive dashboard, which was just demonstrated. Finally, we will go through some future work. Right now, we are working on a user study of this tool in a class at UIUC CS411. This is a database systems course, fast-paced, challenging, with a large class size, the exact environment the tool was designed for, essentially, though certainly we expect that it would extend to less demanding environments with fewer students as well. We intend to structure this as an in-class programming assignment, followed by a review session conducted through Echelon in the format covered previously. Ideally, this will help the students address any misconceptions they have about structured query language. In addition, it should improve their confidence, since rather than going through machine problems, iterating on a starting solution with no conception of whether this is the right path, we help them find out afterwards, was their solution on the right track? If not, what can they change about it? What can they come to understand about SQL that will help them be a better database programmer in the future? We intend to evaluate this both through a survey of students' reactions and opinions, and also by a more empirical study that, by clustering the submissions to a similar question on the final exam, both in this semester and a previous semester, we can compare the queries associated with malformed or incorrect assumptions about SQL, and our hope is that the clusters that are undesirable will shrink in size relative to previous semesters as a result of this review session. Anyways, we hope you enjoyed our presentation. Our contact information can be found below, and if you have any questions, I would be happy to answer them, as would, I'm sure, my co-authors. Thank you.